Okay, so welcome to the very last session of what's been an awesome wafer so far. This session is on multi-robot systems. And our first talk is by Ramon Iglesias. And let's go ahead and get started.
All right, thank you. Hi all, I'm Ramon Iglesias, and I'm going to talk to you about our work in autonomous mobility on demand systems, which is basically large fleets of robotaxis servicing passenger requests. This is joint work with Federico Rossi, Rick Shang, and under the supervision of Marco Pavone. So when we talk about autonomous mobility on demand systems, what we mean is imagine any of the existing mobility on demand services in which all of their cars are autonomous. Now, obviously, there are a bunch of advantages for having self-driving cars, but when you have large fleets of them, you have multiplicative benefits. Specifically, we're going to focus on two issues that autonomy can help with and that we're going to address in this work. They are vehicle availability. That is, when you want a car, what's the likelihood that you'll find an available car? This is a huge issue in current mobility on demand services because vehicles tend to accumulate in one of the areas or stations and deplete the other stations from it. And the other one is road congestion, which I'm sure you all aware of what that is. But the idea is if we have a large fleet of autonomous vehicles, we can also coordinate them such that we minimize traffic. Now, this is a hot topic, so there's plenty of work around. But it's relevant to this paper and this talk, we can bucket up in three types of models. One is queuing theoretical models that capture the stochasticity of the system and then allow the modeler to come up with optimal rebalancing policies. But thus far, no one has been able to capture the congestion part. The other one is network flow models, where they also come up with rebalancing policies, and they do include congestion, but they tend to be deterministic. So we lose some of the nice randomness properties. And finally, there are simulation-based approaches that are good for finding out how the system is going to perform. But the rebalancing is made out of basic heuristics. So what we're proposing today is a queuing theoretical framework that does account for congestion and that it lends itself for a nice optimization. We're going to show you how to characterize the performance metrics, which is vehicle availability and the amount of vehicles on the road. And we're going to show a method to find congestion-aware routing and rebalancing policies that are asymptotically optimal with the size of the fleet. So let's get into the model. Imagine you have N stations in an urban environment connected by a network of roads. You have M vehicles servicing passenger requests. Customers arrive to station I with the intention of going to station J as a time-invariant Poisson process with rate lambda ij. On arrival, if the customer finds a vehicle, he boards the vehicle, and the vehicle self-drivingly takes them to the destination. If there's no vehicle, then the passenger gets angry and leaves the system. This is what we call the passenger loss model. It's one of the key assumptions. Now, we can look at this as a queue. Basically, if we consider that the vehicles are the ones waiting for the passengers to arrive, they form a queuing phenomenon. We consider them to be served once the passenger arrives and takes them. So we've modeled the stations as single server queues. On the other hand, we model roads as infinite servers. This seems a little bit odd because we're talking about congestion. So let's imagine we have by infinite servers, let's imagine we have infinite lanes. We're going to I'm going to talk about in a bit how we're going to address congestion. But for now, let's assume that the number of vehicles in a road does not affect the travel time of the other vehicles. Now, thus far, this is in line with what other queuing models have done. To be able to capture how many vehicles are in each road, we want to inject a notion of classes. Basically, for each origin-destination pair, that is for every source and every target, we create a class. We give it a class. And for each class, we give it a routing matrix. That way, we can define how the vehicle is going to traverse around the environment. Under these conditions, with the single servers, the infinite servers, a fixed number of vehicles, and the classes, this becomes a BCMP queuing network, which is a well-studied, well-known framework for queuing theory, in queuing theory. The beauty of BCMP networks is that you can characterize the probability, the stationary distribution in closed form. However, the performance metrics that we're looking for are still not, you cannot compute it right off the bat yet. They are, in fact, functions of our normalization constant, which is a bit expensive to compute as the size of the network grows. However, there are iterative methods to compute this exactly. Now, we made several assumptions on this model. Basically that the rate at which customers arrive is time invariant. We justify this by looking at this graph. This is, on the y-axis, the average number of pickups in New York City, and on the x-axis, the time of the day. We see that this average number changes a lot slower than what the average trip duration is. So basically, when we're talking about the steady state distribution, we're talking about a tiny segment or a segment of the day. We also talk about the passenger loss model, where the passenger leaves if there's no vehicle. This has the nice property of decoupling the queuing phenomena of the vehicles and the passengers, but it seems like a crude assumption. However, we're going to justify it by saying that we are aiming for high quality of service systems and relatively large fleets. Finally, we talked about infinite service and how congestion wasn't, and the number of vehicles wasn't affecting congestion. But in fact, in traditional traffic theory, congestion starts after a certain nominal capacity, and then it starts making its toll. So what we're going to do is we're going to assume that the travel times are unaffected up and until that nominal capacity, and we're going to try to keep the number of vehicles in the road within the nominal capacity so that this assumption works. That said, let's go to objective. We want to find a rate of rebalancing vehicles, so how often does a vehicle go from, it goes empty from station I to station J, and a set of routing matrices for all these OD pairs, such that we minimize the expected traffic in the system. Subject to the fact that all the availabilities in all stations is the same, and that the traffic or the expected number of vehicles in each road is within the capacity. We also have other constraints such that the vehicles, when they leave their source, they have to reach the target. Everything that goes into a queue goes out of the queue, and the transition metrics are probability measures, and so on and so forth. But the top three are the important ones. Now, at this point, there's a little issue. Basically, the actual throughputs are a nonlinear function of our rebalancing rates and our routing matrices, which makes this a little bit complicated. However, we're going to exploit a little trick here. In systems which are balanced, in networks which are balanced, the availability at the stations becomes 1 as the number of vehicles goes to infinity. This, in turn, makes our network from a closed network to an open network in queuing terms, and makes our actual throughputs, not only we can get them right off the bat, but now we can make them our decision variables. So now we're optimizing with respect to the actual throughputs. This makes our problem much, much easier and makes it a linear program, which is quite scalable. Additionally, we can also characterize the number of vehicles at each road, which means that, which becomes a Poisson distribution, which means that we can not only constrain an expectation, but we constrain that what is the maximum probability tolerable for which we accept that the nominal capacity be exceeded. We tested this method in a model of Manhattan with 1,000 roads and around 50 stations. And we trained the travel demands and travel patterns with New York City's taxi open dataset. And we tried two scenarios, one where we're constraining on expectation, and another where we don't want any road to ever, we want the maximum probability of exceeding the nominal capacity at any road to be at most 10%. These are the flows, the resulting flows for that probabilistic bound. As expected, most of the traffic happens here around the center of Manhattan. Now, in this graph, we have the road utilization. Basically, at this point, we are at nominal capacity, and the fleet size. This is for one specific road. We see that as the fleet size increases, if you're constraining on expectation, there's a high likelihood that you will exceed the nominal capacity and thus violate your original assumption. However, by setting probabilistic bounds, this becomes less and less likely. One would think, but this is very conservative. But in reality, our objective function, which was to minimize traffic overall, is rather unaffected. Not shown in any of the graphs. The difference of expected traffic or amount of vehicles in the road is less than 1% difference from one to the other. This means that the algorithm was able to find extra capacity in roads in the vicinity. We wanted to test how good our assumption was of constant travel times. What we see here is we have on the x-axis what deterministic time travel would have been. That is, if congestion doesn't affect our travel time, how much would it take from going from one origin to one destination? Every dot is a OD pair. And then the y-axis is the increase once you take into account congestion using traditional traffic theory methods. And we see that at most, we have 8% in the scenario that's based on expectation, and around 4% at most in the probabilistic scenario, which both are quite encouraging. Now, our favorite slide of the conference, the Durling boundary. First, this model and this optimization is set for steady-state distribution. If you want to go and try it at home, I recommend that you complement it with a real-time policy. The congestion model is a bit crude, I admit it. But in the future, we intend to include load-dependent queues. Also, the passenger loss assumption works very well when you have large fleets and we have large availabilities, but it tends to lose a lot of information in low availabilities because you're completely disregarding the fact that passengers can wait. In the future, we want to interact with public transit and see how this interaction might work. And we're actually working on integrating large fleets of autonomous and electric vehicles so that they can serve ancillary services to the power grid. With that, I would like to thank you all for hearing me, and I would like to thank Toyota and SF for sponsoring. I'm open for questions. Thank you.
Thank you. So, question?
Thank you. Great talk and interesting problem. Can you comment on the robustness of your solution? What happens, especially if you have a dynamic road network with time-varying road capacities and some of the roads may be blocked and so on? So how your proposed algorithm will work in that case?
So let me see if I understand. So you want to know if some of the roads are blocked?
Or their capacity is changing because there is already some existing traffic in
so
this city.
We can assume, it depends on how, I mean, again, this is not for a real-time policy, right? We're still just assuming steady state distribution. But if we want to model exogenous capacity or a roadblock, we restrict the capacity of that road, the nominal capacity. Right now, the main concern is endogenous congestion, thus the traffic that we ourselves are making. But we actually did it here, we reduce the capacities of the road to assume that there's other vehicles along us. And in this way, we're still within this crude assumption that everything is constant up to that nominal capacity, but it's a first-order approximation anyway.
What about, again, in similar notion, what happens if you have a time-varying, passenger demand instead of your assumption on, constant customer demand? How your proposed algorithm will work in that case?
I see. I wouldn't know. That's something that would be interesting to see. Previously, what we looked at is, let's say if you have 24 hours in a day, something we'll look at is like, okay, just plan to see how it will look at each of the time steps. So discretize the day and find how the distribution will look for each of those days. Again, we're assuming that the change is rather small for the change at which customers arrive changes rather small compared to the rest of the system. So what we've tried or sort of address this is by discretizing the day.
So let's have the next speaker start setting up while we take another question. Other question?
How does the size of the LP scale with the road network?
That's a great question. So we have a number of classes times the number of roads. So it grows in that order. It's the time. So you have the number of variables is the number of classes times the number of roads. In classes, it's OD pairs. Does that make sense?
Okay, so let's go ahead and have a switch of speakers. Is there any other question while we're making the switch. Back here?
Oops.
One of the assumptions you made early on was that all the stations have the same number of passengers per ride, if I recall correctly. I thought that would be lambda. That's a misunderstanding of what you did.
No, we are assuming that the rate at which customers arrive to the stations doesn't change. But the rate of arrival at each of the stations is definitely different from one another. In fact, there are some stations who we might have 0 passengers arriving, but because their vehicle, they might be a destination for other stations, they might have vehicles that are there, and then you have to move those vehicles back. So there is obviously a discrepancy around the network for all the stations.
Okay, well, let's thank Ramon again. Great
All
talk.
right, thank you.